take them down and take them down and take them down, take them down, take them down and take them down and take them down. As you look, the whole room explode down and thick of you, thick of you. As you look, the whole room explode down and.
So, this talk is about concurrency, concurrency in Scala, and in particular using the Akka library with Scala to write programs that can run concurrently on multiple CPU machines. Akka can also be used to write distributed programs, but we're not going to cover it in this talk. Maybe one sentence about myself. My name is Yardena Meymann. I'm right now a software architect at VMware, and
they just announced the JVM drags.
Oh,
it's probably going to be like that
so
for another
maybe if wait a minute.
Zase FSK?
Ale żeś tam,
I think we can, well, let's start with the first, the first slides aren't that important, so it's okay if people will join later on. So I've been programming in Java forever, since version 1.0, too long, mostly in the area of server-side applications, working with databases, but also distributed systems. At some point I realized that I'm not too satisfied with the toolset that I have in Java, so I decided to learn Scala, and I mostly learned Scala during my work on the master's degree, so it was in an academic context, but then when I returned to the industry, I thought that using Scala in the industry would be also very helpful, and Scala can help me solve real problems, and that's what I'm going to show here, sort of a showcase of how Scala and Akka can help solve real-life problems. So why are we talking about scalability? Everything gets bigger and bigger. We need to solve bigger problems. There's more data. Everything gets big. And when we need to solve a problem, today we usually divide the problems into smaller pieces because we want to be able to leverage both multiple CPUs and multiple cores on a single computer, or leverage many computers in a data center. These are basically two types of distributed programming problems. So we both need concurrency. Concurrency is basically running on a multiple CPU machine, so we still have a single memory space, but we want to leverage multiple CPUs. And the second issue is really distributed computing, where we have many machines that need to work together to solve a hard problem. So just a few words in the introduction of the terms that I'm going to talk about here. So what is Scala? Scala is a general purpose programming language for the JVM, developed by Martin Nedersky at Lausanne Polytechnic Institute. Martin Nedersky worked previously on Java compiler and on Java generics, so he knows JVM very well. And at some point he decided to write a better language for the JVM, and that's how Scala came about. Scala is a hybrid language. It's functional and object-oriented. So you have first-class functions and many things that you have to have in a functional language. It's not a pure functional language, but it's closer to what you'll get in, say, Ruby, C#. And object-oriented, it's actually taking a step forward from Java towards a better object orientation as well. For example, there is no primitives, there is no static, so some of the things which are sort of sins or legacy features of procedural programming that we still have in Java, Scala is trying to eliminate those and instead bring new features from the functional space. Scala is type safe, so on top JVM there are many excellent languages. There is Groovy, and there is Clojure, and there are other languages, of course, there's JRuby and Jython, but there's not too many. There's Kotlin and a bunch of others, but there are not too many type safe languages, languages that are checked for type safety at compile time. So Kotlin does have type safety to some extent. Scala is very type safe. So type safety is something that is not Boolean really. You can have a more evolved type system or a simpler type system. And Scala has a very evolved type system. So the idea is basically that you can check as many things at compile time as possible. What it also, another advantage that it gives is a good performance. So Scala is generally more or less one-to-one, in a one-to-one ratio with the Java performance, compiles into very efficient bytecodes, and it leverages type safety and compile time type information to do that. So this is one of the features of Scala which gives it also sort of an advantage in comparison to other JVM languages. Scala is very powerful. It's a large language with many features. It's concise. The programs are short. I heard a survey that found out that Scala programs are usually twice shorter than equivalent Java programs. It's extensible. It allows you to extend code. It may not go as far as, let's say, Ruby or Python or Groovy in the ability to extend code, but you can change code at runtime to some extent, and definitely better than in Java within the language. I'm not talking about the toolset here. The language itself allows you to do that. And there's quite good interoperability with Java, again, because Martin Nadersky originally comes from the Java compiler team, so he knows what he's doing. And there are issues there, but generally the interoperability is quite good. So this is Scala. And Akka is actually a library, which now is getting more and more tightly integrated with Scala. Originally, the library can be used both in Java and in Scala. And what I'm going to show right now is Scala integration. So I'll use Akka with Scala, and in particular, I'll use the latest version of Akka, which is 2.1, with latest version of Scala, which is 2.10. The Akka toolkit actually allows us to build programs that are, well, let's say, we can later distribute, or we can run concurrently. And it gives us special semantics of actors that allows us to write both concurrent and distributed programs in an easier way than what we used to, because we used to working with threads, we used to working with shared state, and what shared state brings us to is race conditions. It requires locking, and the programs get more and more complex. For example, I think Brian Gotts, one of the people who wrote the Java concurrency in practice book, he said, well, if writing writing a good program is hard, writing a good concurrent program is much harder, and writing a completely correct and efficient concurrent program is really an art. And in today's world, it doesn't it can't be an art, because we all need to do it. We want tools that will make this problem simpler to solve for us. So Akka is, I believe, such a tool. It provides a very good abstraction for writing correct and efficient concurrent programs. So what are actors? Actors it began in Carl Hewitt's research in the 70s, and it's actually a different model of dealing with concurrency. So we have a shared state model with threads, and actors is a different model. And it started as a research project, but today there are actually many systems or quite a few systems that use this paradigm and result in very good, very resilient and efficient systems. For example, if you heard of the Erlang programming language, it's based around this actor paradigm. So what is an actor? Actor has a local state. So we have state, but we don't share it. Every actor has its own state, and the rest of the world doesn't see it. How do they communicate? Well, they send messages to each other, and messages are immutable pieces of information. Each actor has a mailbox. So we send messages to the actor's mailbox. All the logic is encoded in the receive function of the actor. So the actor receives messages, and the reaction of the actor to the message is actually where the logic resides. And usually actors, they don't come in one. They usually come in systems, and in the way they interoperate. This is where our program actually is. It's in the interoperation between actors. So some of the good properties of actors, we can add actors or kill actors at runtime. Akka actors are very lightweight. This is again from one of the benchmarks of the Akka team. You can change actor on the fly, and it's again built into the actor. I'm not talking about some external solutions. And actors can be both local and distributed. So we have the same API, but an actor can be on our machine and then it's a local actor, or it can be a remote actor somewhere in a different machine in a cluster. So I'm going to show, sort of give you a showcase of actors based on a small project that I did. So it started from something that I had to do I had to do at work, I then thought, well, it would be really cool to convert this to Scala and Akka, and the things I learned in the process is what I'm going to show you here. So the tool itself, I call it Scotchdog because of sort of a Scala watchdog. It's like a small monet. If you know what monet is, it's a tool that monitors services in your box, and if the service is down, then it starts it up again. So it's like a little daemon and watchdog, whatever term you use. But why not use Monet? I needed a tool which is cross-platform, and unfortunately we still have programs that have to run on not just Linuxes but on Windows, that was one of the main use cases here. So I wanted to be JVM based because our server already have several JVM based processes, so we have Java there. And so I don't need to install anything else. So that was the solution. And why Akka and Scala? I wanted it to be resilient. I want everything to be asynchronous because the watchdog is no good if the watchdog itself stops or crashes, definitely, or gets stuck when talking to one of the services. It doesn't help much. So basically what it does, you configure a list of services. If you saw Monet, you know it's Monet sort of like monetrc file. So you can start and stop services through the watchdog, and you can also get the status of services, and the watchdog ensures that they are all up.
Where does the distribution fit in? So
distribution here, there's no distribution here. I'm going to talk about concurrency right now, not about distribution, not about like real parallelism of several machines. This is still within a single machine. What I want to do is I want to create an actor per service and an actor for the watchdog, so something like this. Now, if I'm using Akka, then I have a slightly bigger hierarchy, and hierarchy plays a very important role in Akka. So all the actors, they have to be arranged in a hierarchy. This is also known as a supervision hierarchy. So by default, Akka comes with a root actor, an actor that supervises over the whole system. Then I have two child actors, one user for all the user actors, so it supervises all the user space, and system actor that supervises over all the system actors. So my watchdog, because it's a top-level user actor, is going to sit under the user element in this supervision hierarchy. So this concept comes from Erlang and OTP, and what it does is for each actor, we have its supervisor watching over it. So we have like a built-in watchdog in the system. So if an actor fails for some reason, the philosophy is let it crash. We're not trying to deal with an error within the actor itself. We're just notifying the supervisor that something went wrong. And we let supervisor deal with the problem instead of dealing with the problem ourselves. Why is this important? Basically, it's easier to work in a concurrent way like this. Okay, it's harder to do recovery from failure without going into race condition and state problems. So it's actually basically for the purpose of easier concurrency. So what we have is a supervisor can get this message of something went wrong with one of my children actors. It can resume the actor. By resuming the actor, I mean the actor sends its state to the parent, and then the parent says, okay, I'm going to recreate the state of the actor and restart it. Okay, so there's no mending of states. The actors cannot like send their hand into someone else's state and start messing with it. It's all messages. Okay, so this is the restart. Obviously, sorry, this is the resume. Restart is obviously the actor is going to be restarted with a fresh start, with a fresh state. And there is, of course, termination or propagation of the error to the higher elements in the hierarchy. And there's different strategies for recovery. We have one-for-one and one-for-all strategy. One-for-one means that if an error happened in one child actor, I'm going to deal with that actor. I'm going to restart it or resume it. And one-for-all means that if something happened to one of my children, I'm going to deal with them all, restart them all, or maybe resume them all. And it's a bit of an imaginary scenario, but if you look at Monit, for example, you can define dependency between services. Sometimes you want to say, if some service restarted, there are other services that need to be restarted as well, because it was a basis for other services. So one for all is something that can be used in such a case. Okay, so let's start building the system. I'll start with messages. First, we want to define the messages. So if we have a service, so the commands would be like start, stop, is started, or monitor, unmonitor. For the watchdog, we'll also have a start. We'll have an add service to add service to the watchdog and do something for a specific service, and maybe we'll see some more commands. This is just a partial list. How do we define this in Scala? In Scala, we use here mostly case classes and case objects. So the sealed trait on the top trait is like an interface, like a Java interface, and sealed means that it can be extended only in the current file. So it's sort of like a package private. Probably the closest thing to it in Java would be package private, but here it's private to the file. And then we have here case object. So Scala has special construct for value objects that we need to make immutable. They're called case classes. They give us several nice features. So we have immutable members. We have pattern match. We have copy on write. We have equals and hash code and several more nice properties to them. And here we use case object because there's no parameter. So it's effectively a singleton. Each one of them is a singleton. It's like an enum, really. And this is how we define them in Scala, and each one of them implements the service command interface, so later we can relate to this whole family of commands. So we said case classes and case objects. This is what we want to use for messages. For watchdog commands, they are a little bit more interesting. So we have a start watching with this, which is also like a singleton. And an add service, for example, already needs parameters because we need to say what is the configuration for the service that we need to add. So let's say we have a service configuration object, which would also need to be immutable, obviously, and probably also a case class. And when we add the service, we pass this as a parameter inside the add service message. Another command is a per service command. Needs two parameters. One is a string of what service we want to do this command on, and the second is the command itself. So how do we send messages? We send messages in Akka basically in two ways. There is a tell and an ask command. Tell, also known as a bang, and coming from Yatsvi's enjoying this, coming from Erlang. So there used to be bang and bang bang and bang bang bang, but no more banging. Just tell and ask. So tell sends a message asynchronously and returns immediately, and ask also returns immediately, but it gives you back a future. If you're familiar with Java futures, the basic concept is the same. You get back a future, and then you can retrieve the value from the future. So this is the ask. You can use the ask command or ask operator, both in words, and I'm going to use the operators from now on. Okay, so tell and ask. Okay, so now we have messages, we have ways to send messages. We need actors. We need to define our actors. So what we do here is we define an actor class. Class, just like in Java, you have constructor parameters on top. We're taking a configuration for each service to define the service actor, and it extends an actor, which is a class that Akka provides us. And what actor gives us, it gives us several functions. We can create other actors. With actor, we can get an access to ourselves, a reference to the actor that was created by me. A sender of the last message we also get, and several lifecycle hooks. So I can write my own hooks for when the actor started, when the actor died, things like that. But the main thing that we need to override in the actor, we get an abstract, a receive method, and we need to override it. And here is where the code that handles the messages. Here's the logic. So for example, for the service, we're going to have something like def receive. This is the definition of the method. It overrides. We can also say, write an override keyword here. I didn't. And within the receive, sorry, we have a pattern match expression. Sort of like a switch, if you haven't seen anything like that before. So we're saying, okay, if we got a start message, we're going to do what is needed for a start operation. If we got a stop message, we're going to do the stopping. If we got a started message, we're going to perform the actions that we want to perform. And then we want to reply to the sender with the result of the operation. So what we do is sender tell result, and this is going this will send the result to the actor who originally sent the message to us. So receive is based on Scala's feature of pattern matching. It uses it extensively. We'll see more examples later on. That was the service actor, but we will probably start with the watchdog actor. That's the top level actor. How do we create an actor, a top level actor? First of all, we need an access to the actor system, and that we get from creating an instance of actor system with a certain name. And then we ask the system to create a top-level actor for us. And creating top-level actors is done with the actor of method. It takes configuration, and we can provide a name for the actor. And we'll see how it's useful in the next slides. What we get back is an actor reference. We never get hold of the actor itself. Because like I said earlier, you can replace an actor. You can kill an actor and restart it. So we don't want people to have a hold of the actor instance itself. We want an additional level of indirection here. So what we when we communicate with actors, we talk with the actor ref actually, not with the actor itself. Here we use a default constructor. We'll see it in another example in the next slide. And properties allow you to customize several things for the actor. One of the things is, for example, the dispatcher, which is basically the execution strategies. Right? And if you use Java till concurrent, you know that there are several types of executors, and you can choose one. So Akka is very, very flexible. In comparison to, for example, Scala's stdlib actors, which was previously part of Scala, now Akka is becoming the official actor system for Scala. But not every actor system is actually as configurable as Akka. And this is one of the important configurations that we have. We can configure the dispatcher, we can configure the mailbox implementation, and several other things. So here is another example of receive. This is the watchdog receive. So what we see here is that when we add a service, we want to create a new actor for the service. But now we're not creating a top-level actor. We're creating an actor who's going to be a child of the watchdog. So we're doing it using the watchdog context. So each actor has a context. And when I'm creating a new actor using the actor's context, it automatically becomes a child of the current actor. And here I'm also providing a non-default constructor for the actor. So remember, the actor needed to take a configuration as a parameter. So I can provide it here using non-default constructor. And in the end, I have a name of the actor. So the actor has a name. And I started with sending a monitor command to the service. That's the add service. The second command is a per service command. So it's anything I can do given a service name. So what I want to do here is I want to find the actor for the service and then forward him the command. So what I'm using here is I'm using actor for. Actor for allows you to look up an existing actor. And here's why name is important. So if you've given a name to an actor, now using that name, you can look it up with actor for and get a reference to the actor. Then you can forward the command to the child actor. Okay, so we'll start moving faster here. The time is pressing. So as we said, top-level actors are under the system, and we can find actors with actor for. And actor ref is useful because we can also exchange it between actors. It's an immutable class. We can send actor ref to another actor. For example, what would forward do? It would send the sender of the original method, forward it to the child actor, and then the response from the child actor would go directly to the actor that called us. Okay, futures. So fine, we get a futures. How do we extract data from the future? There are several ways. I'm showing two here. One is waiting with a timeout. It's pretty much what we do with Java till concurrent. And another way is it is new in Scala 2.10, allowing you to define callbacks on success and failure of the future. This is the on complete. You have an on success and on failure to define just part of the callback.
What happens when the timeout pass? Is there an interrupt or something?
Well, you with the timeout passes in this case, you get a failure with a certain timeout exception. So again, you can deal with it any way you usually deal with failures.
And it's not running on a different thread, right?
What do you mean?
The actor. is running on a different thread or not?
You don't have to have an actor a thread per actor.
Okay.
It doesn't necessarily happen. So it is actually based on the dispatcher. Yeah, you control it with the dispatcher strategy. Dispatcher strategy is where you control if you have a thread per actor or not, or if you have a dispatching to thread pool. And usually you're the thread pool. Okay. So what I wanted to show here is that it's not important that the actor state, that internal actor state is actually immutable. Internal actor state can be mutable and should be mutable. There's no problem. So for example, I want to invoke an operation which is, are all my services started? So how do I do that? I'm define actually a mutable list for services, and every time I add a service, I change the list. Then when I want to ask all the services for their status, I basically, for iteration, I just go over the services. I send each and one of them the is-started message, and then what I get back is a list of futures. And what Akka gives me, it's something that became in Scala 2.10 a Scala library function actually. You can just give the list of the futures to a library function, and it will wait for you until all the futures complete or fail, and give you a single response. And so, so this is very easy, very nice utility, used here with the future reduce. Maybe just a couple of words. There is a built-in scheduler. There are many other features I'm not covering, and what we actually want to do in this watchdog, we don't want to poll every time. We need a scheduler to poll periodically, and when someone asks, is the service up or down, we only want the status. So here's another example. I have several vars. Vars is a non-immutable, mutable variable actually inside the actor. It's a local state, so within receive method, I can read and write it freely because I know there's not going to be any race conditions on the receive. Receive is always serial, right? Because I'm working over messages in my mailbox, so it's always serial. So this is an example of using of scheduler, very simple. There are further improvements. What I actually ended up implementing is a finite state machine. You have a utility to do state machines in Akka, and it's also very easy. So your input is not just the message, it's also the internal state, and then you decide what to do based on these two things. That's it basically. I hope I showed you enough of Akka to get your interest. Try this out. You can use it directly. You can use it as integrated with Apache Camel or ZeroMQ, or it's actually the engine underneath the Play framework. So there's Akka in many areas. And these are the resources to read more about it. And since our time is short, we'll stop it here. Thank you very much. And